was a commercial reality at this point. So, welcome to the second plenary talk, and I'm Adrish Banerjee from IIT Kanpur, and it's my pleasure to introduce Dr. Rohit Kapoor. Rohit did his bachelor's from IIT Roorkee in 1999, and then he did his PhD from UCLA in 2003. In 2003, he joined the R&D department at Qualcomm San Diego, where he worked. I think I don't know. And so 15 years he worked in Qualcomm San Diego, and in 2015 he came back to Qualcomm India at Bangalore, where he has been working on technologies and standardization design for 4G, 3G networks. Today he's going to talk about how we can make 5G new radio a commercial reality. So,
thank you. Alright, yeah, sorry for the delay, guys. Looks like even in this day of advanced technology, we can't share a file. But anyway, I guess let's get started. So I really appreciate the opportunity, that I have to talk here, and also in particular because this is an IIT, so a lot of students here, and I guess it's a while since I was a bachelor student, maybe a couple of decades back or something. But I think one thing I do want to get out of this talk, other than the other than sort of the topic of this talk itself, which is basically on 5G, is that I'll take a couple of slides here and there and try to kind of talk about how R&D, how we really do R&D in the industry, especially in this area of telecommunications, right? And with a lot of students being here, I think my hope is that you guys go away with some appreciation for what is it that we do, right? When we say, oh, we add new technologies to 3G, 4G, 5G, how do we do that? What problems do we work on? How do we go about, what's our process, right? How do we go about figuring out if something works or something doesn't, right? So that's kind of one thing I'll try to get out of this, and hopefully, you guys go away with, with a little bit better understanding of the industry as well. But coming back to sort of the main topic of this talk, so as you see, the focus here is on 5G, which I'll claim is a unified and more capable air interface. And the idea behind that is that there's a lot of stuff, there's a lot of enhancements that have happened in 3G and 4G. And what I'm going to talk about is, what is 5G trying to do, right? So I'm not going to go into a lot of details of technology, but what I'm going to try to touch upon is what are the use cases that 5G is trying to address that are maybe a little bit different than 3G and 4G, or maybe a little bit improvements upon them, for example, right? What are, for example, the new industries that 5G is trying to enable, right? In terms of user experience, what are the new user experiences that 5G is trying to enable that maybe 3G and 4G have taken some steps towards, but 5G is kind of trying to take it to the next level. And what I'll do is in the next slide, I'll give a little bit of a historical perspective about how we got here, right? What was 2G, 3G, 4G all about, and then what steps is 5G trying to take, right? And finally, as I said, I hope you sort of come away with the impression that 5G is kind of this umbrella air interface, which is really trying to accommodate a lot of diverse design requirements across different use cases, different user experiences, and so on. So yeah, really that's sort of going to be my focus. And as I said, I hope students also take away something a little bit more nuanced understanding of what happens in the industry from this talk. Alright, so no surprises here. I guess mobile is the largest technology platform in human history. And few things I'll mention here, other than what's kind of captured on the slides, is that there's sort of this generational leap that's been happening every 10 years or so. So if you see 80s, 90s, 2000s, 2010s, though of late people tell me it's accelerated a bit, right? It's probably more like 7 to 8 years that we are moving from from 1G to the next G, right? But I think what's sort of interesting to think about a little bit is that it's really not that far back when mobile data started, right? Actually, I joined Qualcomm in sort of the early 2000s in 2003, and there was a lot of excitement then about how to get mobile data to work, right? And this was the first time that packet switch air interfaces were being designed, were being tested, commercialized, right? And as I said, not too far back, only about less than 15 years back, right? And I still remember that the first air interface that we worked on, packet switch air interface, which was EVDO, the rates that we were talking about, which seemed plenty to people at that time, were tens of kbps on the uplink and hundreds of kbps on the downlink, right? And I think today people will just laugh at that, right? But I think just keep in mind that's not that far back, right? It's less than 15 years back. So just look at how far we've come in 15 years, right? So I hope that gives you guys an idea of just the pace of progress that's happening in this industry, right? And of course, we're not sitting idle. We continue to sort of move that forward. A couple of other interesting things I want to mention here is that along the way, as we kind of sort of worked on this mobile data air interface, there was a lot of interesting problems to be solved as well. And a lot of you are IC communication students here. So in fact, even the basic concept of a mobile feeding back a channel estimate and a base station scheduling some kind of an optimum rate or the right type of data based on that, even that as a concept, or at least as a commercial reality, is only about 15 years old. So it's really not that far back, right? So just something to keep in mind, right? So as I said, when I joined, a lot of this stuff was happening. Then what happened was that EVDO happened, HSPA plus happened. We gradually bumped up the rates. We went to hundreds of kbps, megabits, tens of megabits, and so on. And then with LTE we went even further. We went to hundreds of megabits. We managed to bring down latency even further, right? So a lot of interesting use cases opened up, right? And now we are kind of at the point where there is this entire new set of applications that are starting to come up, right? And I'll talk about them a little bit more. But basically there's sort of multiple things that are happening at the same time, and what's happening on the one side is that in terms of user experience, there's a lot of interest in new applications such as virtual reality, augmented reality, and I've played with some of this myself, in some of the research labs we have. The user experience is just phenomenal there, right? And I really feel in a matter of few years, these things are going to start to become reality, and the type of data rates and latencies they require are just amazing, right? I mean, we are not there yet. We haven't been able to solve that problem, right? So that's really one sort of key area that 5G needs to address, right? How do you go and bump up the data rates even more, get the latencies even lower, to try to accommodate those types of user experiences, right? So that's kind of one direction, right? The other thing that's happening is that there's a lot of other industries which are looking to harness the power of cellular, right? And you guys have probably heard about it a lot. There's this whole discussion nowadays about Internet of Things, how to get billions of devices connected to the internet. But what's starting to happen now with LTE is that some of that is starting to become a reality, right? So we are actually starting to see traction for cellular-based IoT devices. But what's also happening is that that has just whet the appetite of the industry, because what the industry now wants is even more challenging requirements, and I'll talk about some of that, right? So which basically means even more reduced latencies, better power consumption, right? So 5G really has to be a lot of things, right? It has to solve this user experience problem. It has to sort of enable technologies to address this different set of use cases for IoT and some others that I'll talk about as well, right? So keep that in mind. So as I said, 5G, I really think of it as some kind of an umbrella evolution of an air interface, because it has to solve very diverse set of use cases. So yeah, so that's so I think I guess you guys must have seen a lot of this data as well. It's really interesting actually. I remember maybe about 5 years back, in fact Qualcomm CTO had made this prediction that mobile data is going to double every year, right? And then if you do just some simple math, in 10 years that becomes 1000x, right? And that seems like a really, really large number compared to 5 years back. But the funny thing is that it's actually turning out to be true, right? If I look today and compare to 5 years back, or even if we extrapolate based on the trends we are seeing, we're actually seeing a doubling every 2 years, which basically means like 20-30x from where we are right now by about 2020. So that's a lot of data, right? A lot of data that you need to support, right? So that's another interesting use case, right, that 5G needs to handle, right? So now keep all of these requirements in mind, right? A lot of data to support, very good bandwidth latency, right? Extremely good support for IoT technologies. So 5G really needs to be able to satisfy really all of this. Okay, so let's talk a little bit about the user experiences, right? So I mentioned that one sort of key dimension for 5G is to drive this next generation of user experiences. And look at some of this, for example, right? These immersive experiences, right? Some of you have probably had the opportunity to play with these, some of these virtual reality headsets. And in our own Qualcomm labs, there's a lot of work going on in this area. Very interesting the types of experiences you can enable with this, right? And you just have to think about it for 5 minutes, and the potential of this is amazing, right? But again, it requires a lot of support from the air interface, right? So that's kind of one very sort of interesting area. Another big trend that's happening around the world is cloud computing, right? So I'm sure all of you guys are aware of that. But what's really happening here that does impact cellular is that, if you look around the world, a lot of small and medium-sized businesses, they're starting to move their, inventory management databases to the cloud, right? And it's actually starting to happen now because, I've talked to a few people who say a lot of this is happening now, right? So what this is doing now is that, the reason sort of these small and medium-sized businesses may want to do it is because it enables them to harness the power of the cloud, right? So they don't have to worry about maintaining their data, and the cloud also provides them a lot of tools in terms of analytics and other things, which they can then use to figure out exactly what to sell to their customers, right? So very powerful, right? But, right, to make this cloud computing sort of reality really happen, right, you need connectivity such that you don't feel it's there, you should feel like it's like a local access, right? So latencies have to be so tight, right? Reliability and availability have to be so good to enable those kinds of use cases, right? So a lot of very interesting problems to solve, right? So on the other sort of dimension, one was all about user experience. The other thing is that there's a lot of talk about embedding billions of sensors with wireless connectivity, and I think what's really happening is that a lot of it is starting to happen now with LTE, and we'll see an even more increased pace of evolution of this with 5G. But the types of problems that you have to solve here are very different from the types of problems you needed to solve for the for the application in the previous slide, right? So for example, just take an IoT device, right? The typical requirements for an IoT device would be that it should be able to run on, for example, 2 AA batteries for up to 10 years, right? Now this is not typically your smartphone experience, right? Because I know my smartphone dies in half a day, right? So then how do you build these types of technologies as part of 5G, which allow your devices to last so long? So very different problem, right? Likely these devices have very low data rate requirements, but they need to last for a very long time. And the reason for that is that the cost of sending somebody to go and replace that battery is so high, right, that it basically kills this entire industry if you have to do that, right? So you really need these devices to last for a long time, right? The other thing you need to do other than solving the battery problem is that you need to really extend the coverage, because these devices are going to be placed, for example, in your basement, they're going to be placed in areas which are very difficult to reach, right? So then how do you get cellular connectivity down there, right? So you can see now these problems, very different set of requirements from the user experience requirements, right? So another sort of interesting area that is considered a little parallel to IoT is what's called mission critical. And sort of the thing here is that there's a lot of interest in the manufacturing industry in particular in being able to instrument their machines with sensors which have wireless connectivity. So that they can quickly and sort of in a very nimble way be able to control their machines and their devices, right? And the requirements here, a lot of them overlap with IoT, but they are a little bit different too, because here you require extremely low latency, very low latency. These guys are talking about sub-millisecond type latencies to be able to control these machines, right? What it also requires is that your messages have to be extremely reliable, right? So you can see some overlap with IoT, but still there's this whole gamut of requirements that one needs to support, and then you can enable a lot of industries, right? You can enable the user experience, you can enable these new industries. So really 5G needs to be a lot of things, right? It needs to be able to solve all these requirements, right? And I think so that's really sort of, I think, where we see 5G being not necessarily different from, but building on and doing even more than what 3G and 4G have done, for example. Okay. So now that we have all these requirements laid out, so the question is, how do you do this, right? What needs to be done, right? So I mentioned that there are sort of these three critical sets of requirements, if you will. There's the enhanced mobile broadband, right? You need lots of data, very low latency, mission critical services, very low latency, and Internet of Things, which has power requirements, battery requirements, and coverage requirements, and so on. So you need to solve all of these. You have these tools. You have a lot of diverse spectrum, right? And we've typically become accustomed to working in these low bands, right? Maybe a little bit in the medium bands as well. but there's gobs and gobs of spectrum available here, right? And clearly we have to be able to use that to solve some of these problems, right? The problem with that is that this spectrum is really, really hard to use, right? But the point is that if you could use it, right, you could actually make an attempt to solve some of these problems, right? And that's really sort of one key thing that 5G is going to attempt to do. Okay, so I'll talk a little bit about the sort of the types of the types of technologies that are part of 5G or are being discussed as part of 5G, which are going to enable some of these things, right? So let's focus on mobile broadband a little bit, right? So one key thing that we want to enable is millimeter wave. I'll talk a little bit about that in future slides as well. But this is really enabling use of that high frequency spectrum, right? And a lot of challenges in making that happen, right? Now, if you look at IoT, for example, there's a lot of solutions out there that are being discussed in 5G to enable even deeper coverage, even more, sort of enhanced power saving modes to get even more battery life out of the system. And then when it comes to mission critical services, there is this technique of what's called low latency communications, and I'll talk a little bit about that as well. So that's sort of another key, technology idea that's being discussed as part of 5G, right? So yeah. Okay. So let me take a sort of a parallel step and talk a little bit about the standardization of 5G, right? And I'm guessing a lot of students and others also may not be so familiar with how the standards process works. So I'll spend a few minutes on it. So there is this organization called 3GPP, which stands for the Third Generation Partnership Project, because that's when it started, right? Of course, now it's doing 4G and 5G as well. But the idea there is that it's a fairly democratic organization. So many companies are a part of it. Qualcomm, Samsung, many other companies, right? And what happens is that the work in this body works and sort of happens in this way, right? First, there's a problem that some company identifies and says, hey, this is an interesting problem to solve, right? And it goes through a phase called a study item phase, where a lot of companies submit results saying, if we did this problem could be solved, or if we did this, such and such is the complexity of solving the problem, right? So it goes through the study item phase. Once the study item is done and a lot of companies agree that it's a problem worth solving and can be solved in a reasonably complex way, then a work item phase starts. And as part of the work item phase, then different companies bring in solutions. There's usually some kind of a comparison bake-off of different solutions on the usual metrics, SNR, throughput, and so on, right? And some solutions get picked, and then they get standardized, right? So at that point, this 3GPP body, it endorses a solution or a set of solutions for some particular problems. And then, companies both on the mobile side as well as on the base station side, they go and build out these solutions, right? And then they have a lot of interoperability tests with each other to test that the solutions work. So that's how kind of this standards process works. And it's worked, beautifully for the last 15, 20 years or even more actually, right? So now what's happening in the 5G case is that, I guess we are somewhere here, we should be a little bit more to the right, but we are somewhere here, right? Is that there is this mode of 5G called the non-standalone mode. That's mostly standardized. And the reason it's called non-standalone is that this is really a mode which looks at 5G as an add-on on top of a baseline coverage of LTE, right? So the idea is that 5G has access to this tons and tons of bandwidth, millimeter wave in particular. But then a lot of operators have investments already in LTE. So then you could really sort of use this as an add-on on top of that, right? And the reason this becomes compelling is because usually the hardest problems in mobile are solving problems of mobility, right? I mean, data, of course, is you want to get a lot of data across at very high rates, but it's when you have to solve the problem of users moving from cell to cell, still being able to maintain their connections, not having much data outages. Those are really, really hard problems to solve, right? And if you can leverage sort of the existing installation of LTE to handle that for you and just use 5G to give you even more data, right? That makes the sort of the pain of transition a little bit easier, right? So that's where the non-standalone mode comes in, right? And then what's happening sort of almost in parallel and probably will finish sometime this year is the standardization for what's called the standalone mode. So that allows 5G to be deployed standalone, right? And as you can expect, this allows a whole new set of companies that are not operators necessarily today to enter the market with these types of deployments, right? With the standalone deployments. And then beyond that, what's happening is that there's all these work items that are going on. I'll talk about this a little bit more in future slides, which are primarily focused on solving the problem of IoT and mission critical connectivity. Right, so a lot of work going on there. Okay. So what I'll do now is that I'll spend a few slides on talking about what is it that 5G is about, right? So I talked about the requirements, but what are the technologies, what are the techniques that are going to be part of 5G? So I'll focus first on the mobile broadband part, right, as applicable to your smartphone or USB or dongles and so on. And then at a later point, I'll towards the end, I'll talk about what are the new techniques that are going in to support IoT and mission critical devices, right? But let's start with mobile broadband. Okay. So a number of sort of really new techniques are coming into 5G. One very interesting idea that's going to be part of 5G is this concept of scalable OFDM-based air interface. And I'm sure you guys are already familiar with what OFDM is about. But what this really allows you to do is it allows you to kind of scale the subcarrier spacing, right? And I'll show an example of this on the next slide. But at a very high level, what it allows you to do is that if you look at sort of this entire set of frequency bands that we need to support from low to mid to high, there's different amount of bandwidths available, across these different spectra, right? For example, in the high frequency bands, there's lots of spectrum available, right? But then you want to keep your receiver complexity somewhat manageable too. So by playing with the subcarrier spacing, it allows you to kind of handle different amounts of bandwidths while still keeping receiver complexity manageable, right? So that's kind of a key part of it. Another sort of interesting technique is what's called this flexible slot-based framework. So the idea here is that if you we talked about the fact that 5G has to support a lot of these different latency requirements. So you can have different slot structures within your sort of your waveform or air interface, and you can you can have different lengths of these to cater to different latencies. So I'll show an example of that on the next slide as well, right? There's some improvements in coding as well. And then, coming to sort of MIMO, massive MIMO. So, if you look at some of these sort of higher frequency bands in particular, what we really find is that, without doing something like massive MIMO, it's very hard to make use of those frequencies, right? So the question then is that, so 5G is trying to add some interesting techniques to make the use of these more efficient. A key one among them is what's called reciprocity-based MIMO. And the idea is very simple. The idea is that at least for TDD, the idea is that what the base station can do is that it can measure sort of a reference signal that's coming from the mobile, and then use that as the channel estimate for scheduling in the very next slot of the downlink, right? So what that does is that usually there's a if you think about typically how this happens, usually the base station will send you a reference signal, the mobile will measure it, feed it back. So there's a few milliseconds of delay in there, right? Whereas with this, you can sort of turn it around really fast. So it allows for very, very accurate, beamforming, right? And that's really a sort of a prerequisite to make use of these high frequency bands, right? And finally, there are some techniques for handling millimeter wave. And the idea there is, I'll talk about that a little bit more as well. But the idea is that the mobile sort of feeds back some very relevant information across beams, and also that the sort of the air interface structure itself supports some some techniques that allow the mobile to measure these and report them back to the base station. So it can do very, very good beam steering, for example. Okay. So this gives an example of what I was talking about, which is a scalable OFDM numerology. So you can see that if you have your typical 700 megahertz coverage, the typical outdoor macro coverage, right? You can sort of maybe work with this 15 kilohertz of carrier spacing. It's good to cover some of these types of carrier bandwidths, right? But then if you really want to support these 400 megahertz type carrier bandwidths, for example, in the millimeter wave region, right? The sort of the 5G solution allows you to work with a much higher subcarrier spacing, right? And then you can see that it's kind of a continuum. You can sort of scale it depending on your bandwidth requirement, right? And this is really a key thing to make receiver complexity, manageable. So I mentioned about these flexible slot structures, right? So I'll talk about 2-3 of these. So what you see here, what's called the data-centric slot structure, it's really similar to what we have today. The idea being that you have downlink data going sort of in one slot, and uplink data and uplink control going in another slot. That's typically how things are done, right? And uplink control would be, for example, CQI, ACNAX for downlink data, right? But then what you can do is that you can actually do what we call a self-contained slot, right? And the idea is that you can do downlink data, but you can send uplink control at the very end of the same slot, right? And as you can appreciate, this really allows you to cut down latencies, right? Because, for example, if you have to do a retransmission of this, you can send an ACNAC immediately, right? Of course, this does not come free. It has complexity on the receiver side, but the thinking is that to enable some of the use cases that I talked about, this is going to be one of the key sort of techniques to get there, right? I'll show some more details of this on the next slide as well. Another interesting thing that allows you to target even lower latencies, like sub millisecond, like a tenth of a millisecond type latencies, for example, is basically that you can do these mini slots. So what you can do now is that the base station can sort of tell the mobile that, hey, I'm going to only serve you in this fraction of a slot, so don't bother looking anywhere else, and right, and that allows you to cut down the latencies even more, right? Because any packet transmission that arrives right before this, right, the base station can serve it right here, and it gets done by here, right? So that's what we call a mini slot, and this is really sort of very suitable for the mission critical type use cases that I was mentioning about, right? So you can see there's this entire spectrum of this whole flexible set of slots that 5G is planning to support. Okay, so I'll show a couple of other sort of benefits of what we call the self-contained slot, which was right on top of the previous slide. So I mentioned this low latency, which means that you can turn around things really fast. Another sort of advantage of this is, I mentioned this reciprocal channel measurements. So the idea being that you can send your reference signal, this SRS, right here, right, which is at the end of the slot. The base station can make measurements on this, figure out your channel, and then schedule you right away, right? So the turnaround time between doing a channel measurement and then using it for scheduling has become extremely small now, right? And that is a very, very key enabler we find for utilizing some of the massive MIMO, use of massive MIMO in some of the higher frequency bands, right? So that's really key, right? Very big advantage. Again, all of this does not come for free. It has lots of implications on the design of the mobile as well as the design of the base station. But I think what's really happened over time, right, is that hardware capability has also got to a point where we think that these things can be achieved today. I think if we asked us the same question maybe 10 years back, I think nobody would have thought that these things were possible. But today I think we're at the point where where these things may be possible, right? Another interesting thing you can do with this is this adaptive uplink downlink. So the fact that you can sort of share the slot structure also allows you to to very quickly adapt what percentage of bandwidth will go in the uplink versus how much will go in the downlink, right? So that's another sort of key advantage here, right? So overall, this what we call this self-contained slot comes with many advantages, right? Okay, so I talked a little about massive MIMO earlier, and the fact that this channel reciprocity can be used to really sort of very finely pick your beams, right? Another way this that 5G has added some techniques to help this is basically by adding a very high resolution code book in the spatial domain, right? And what this does is that you can really form very narrow beams now if you have this type of precision in the in the code book, for example, right? But again, this comes with receiver impact as well, because it's very hard to solve such a complex code book in software or firmware. So you really need to look at in hardware how can I implement this, because you need to calculate these complex code books and turn them around really fast, right? So you can see very challenging problems to do on the mobile side as well. And then let me talk a little bit about millimeter wave as well. So I mentioned that in one of the earlier slides that basically the the air interface structure itself allows the mobile to kind of report what are the beams it's seeing and sort of feed it back to the to the base station. But sort of the other interesting thing that also allows the use of millimeter wave is this tight integration with sub-6, right? Sub-6 gigahertz, right? Because as I mentioned, millimeter wave is very hard to use it as sort of a baseline underlying spectrum coverage, right? Because it's not very easy to solve problems of mobility and still get the same robustness as you got with sub-6 gigahertz, for example, right? So the thinking is that the way to do it is to look at it as kind of a boost of capacity with sort of the underlying coverage being sub-6 gigahertz, right? And that way we think, along with sort of some other techniques, we think this problem can be handled, and you have a way to leverage this extremely high amount of bandwidth that's available in those high frequency bands, right? So that's kind of another interesting technique. Just one or two other things to mention here is that sort of a common thread you must have seen in some of the earlier things I mentioned as well is that as you start deploying some of these new 5G things, you're really relying on a baseline of provided by either LTE or by 5G itself deployed in sub-6 gigahertz, right? And this is where what we call carrier aggregation really comes in, right? So the idea is that you look at a sub-6 technology as a baseline carrier, and then you add a 5G carrier on top of it, and through the technique of carrier aggregation, right? So which basically really means that the mobile is able to receive two carriers at the same time. You're able to kind of very well use all this spectrum, right? One thing I'll mention is that there was a very interesting sort of technique added in LTE called dual connectivity, and that seems to fit in really well here. So the idea behind dual connectivity was that if you have an LTE macro and an LTE small cell, right? And a small cell could be, for example, something that has the transmit power of a Wi-Fi access point, for example, right? What you could do is that you could simultaneously receive data from both, right? And of course, this has a lot of challenges now because you need a receiver that can sort of beam null, the other stream, right? And a lot of protocol impacts as well because now packets can come out of order. Actually, somebody was showing me a demo today outside as well about this. Anyway, so packets can come out of order from the two streams. But if you can solve it, very, very good potential, right? So we think that these types of techniques would also lend themselves really well to, to deploying millimeter wave with a baseline of sub 6 gigahertz, for example, right? So there's this sort of whole gamut of techniques that I mentioned, but this is really sort of an underpin of how to make all this work, right? At least in the context of enhanced mobile broadband. Right? Okay, so let me do this. I'll spend a couple of slides now on since I promised that there's a lot of students here, so I'll talk about what happens in industry. How do we do R&D really, right? And then I'll go back and talk about what is happening in 5G as well as in LTE to some extent with regards to evolution for IoT devices. Right? So this is kind of what we call the virtuous cycle of R&D and innovation. And really typically how it starts is that somebody articulates a problem that, hey, I want HD video to be supported, or so many streams of HD video to be supported in some manner, right? So you start with that. So you figure out on the air interface what types of techniques you would need to solve it, right? So that's where some of these inventions come in, right? Now, once you have some of these ideas, you have to evaluate them, right? So what happens is that typically we'll have simulations, we'll have analysis, right? Fairly detailed simulators, right? Very, very detailed simulators to figure out how much advantage you can get, from some of these techniques, right? Now, what often happens is that, we see some techniques in simulations and analysis, but then translating that into reality is another big step. In fact, if you ask me, a lot of the engineering really goes there, right? Because having good ideas and establishing them through sims and analysis is one thing, but a big part of the work is translating that into gains, right? A lot of work is required there, right? So what we do is we go and build these proof of concepts like test beds and so on, and we try to see, what are the limitations? Are we seeing anything different from what we saw in simulations, for example, right? And oftentimes we do, right? So we learn from that, we go and put it back and try to improve our simulations as well. But anyway, once we are happy with this, once we are happy with the gains, then we take the step towards standardization. We go to 3GPP and say, hey, this is an interesting area to evolve the standard. So there's the usual discussions there, as I mentioned before. Once that happens, there are typically trials, and trials would be, for example, between a mobile vendor such as Qualcomm and a base station vendor, as an example, Ericsson, right? And then we try to see, hey, whatever we saw in our proof of concept, does it really work in trials? Because what happens with proof of concept, right, is that it's just a proof of concept. But there's a big step again to be taken between proof of concept and making it commercial, right? And a lot of gains, sometimes go away there, because what happens in proof of concept is that sometimes you don't worry too much about boundary conditions, some error cases here and there, but oftentimes they threaten to wipe away the gains as well, right? So we go and do these trials, a lot of learning from them. If everything is okay, we talk to operators, and then the technology gets commercialized, right? But what happens is that even after commercialization, there's learning. In fact, if you look at 3G, 4G, 5G, right, there's a lot of things we did in 3G, and you later realize, maybe we could have done this better, right? And then we take that learning and put it back into 4G then, so that we don't, I shouldn't say make the same mistake, but we do things better for 4G, and then similarly from 4G to 5G, right? So basically there is this whole sort of virtuous cycle of R&D, and that's really what's happened multiple times between over the last 15 years, right? From the beginning of mobile data to really where we are today, right? And I hope that gives you guys some idea. I'm sure a lot of that, or at least some of this, is also done in universities, but then I think the difference is that we have to commercialize too. So yeah, so a lot of effort goes there. Okay. So I'll just to give you guys an idea, right? So there's a lot of different techniques, lot of different new technologies that I've worked on as well, and that Qualcomm has worked on too. But I wanted to kind of just give you guys a flavor of a couple of things, so you guys go back with something to think about. Very interesting problem was the problem of VoLTE, right? And I'll motivate some of this, right? So the idea was that for a long time, the voice that you were getting on your cellular networks was what's called circuit switch speech, right? It's very simple in practice, right? You're assigned a circuit, right? And then you get your voice, packetized voice on top of it, right? Very simple, right? But if you really start to think about, right, it's very inefficient, right? Because what happens is that, say if you're making a conversation with somebody, right, you're quiet half the time, the other person is quiet half the time, but your channel is still assigned to you, right? So there's just a simple thinking will say that, there's at least a 2x gain to be had there. In reality, there's much more, but at least a 2x gain just by dint of that, right? So the question is now, what do you do, right? How can you solve that? So the thinking was, okay, we have this package switch channel, like a big fat pipe such as HSPA, EVDO, LTE, for example. Can we just carry speech on that, right? Yeah, you can, and that'll take away the inefficiency that you get from assigning circuits, right? But then it brings in so many other problems, because what happens is that with circuit switch you had a nice predictable, these voice packets basically get encoded, decoded every 20 milliseconds, so you have this nice predictable behavior, right? But now what happens is with packet switch, right, these voice packets get mixed with data, right? And then you have to solve many problems. You basically need to design a very good scheduler, right, that needs to know, this is a voice packet, I need to put it ahead of data packets, right? And even with that, packets don't come with that 20 millisecond synchronicity, right? So you need something at the receiver to put them back in that 20 millisecond boundary before playing them out, right? So in theory, a lot of gains, right? And in practice also a lot of gains, but a lot of complexity to get there. Very hard problem to solve, right? So just to give you an idea. Another interesting thing that in fact I myself had worked on also was carrier aggregation, right? And the idea, I think the first time this was really done was in the context of HSPA+. So the idea was that you have a 5 MHz carrier, right? A lot of operators had more spectrum as well. So the question was, can you give the mobile 2 5 MHz carriers, for example, right? And that way, not a surprise that you're going to double the mobile's data rate, right? But if you've taken any courses in queuing theory, right, it's a little bit more than that, right? Because what happens is that, of course, you double the user's data rate, right? But then there's trunking gain too, right? Because this becomes equivalent of a shared queue or a shared server system as opposed to having 2 separate servers, right? So you can see that there's going to be some trunking efficiency there to be had. And in fact, what it looks like is that you can support the same user experience for users at a much higher load compared to if you had 2 separate single carrier systems, for example, right? So there's that gain to be had as well, and operators love that, right? Because the big challenge for operators always is that when load starts to go up, clearly your user experience starts to go down. But with something like carrier aggregation, you can use trunking in a lot of interesting ways to some extent keep that gain consistent, right? So just to give you an example, these are the kind of things, at least some of the problems that sort of we worked on and how we approached it. I think maybe I'll take 5 more minutes. Huh? So I guess let's spend a couple of slides talking about what 5G is doing for other than mobile broadband, right? So for the IoT mission critical use cases. So just to give a background, right? As I mentioned with LTE, a lot of enhancements went in, and I'll mention a couple of those too. But with LTE, really this IoT ecosystem is starting to happen now. We are seeing a lot of interest in deploying these IoT devices in a lot of different verticals, a lot of different industries, right? And the type of enhancements that LTE had to bring in to make this ecosystem viable were really in sort of 2-3 different areas. One was, as I mentioned, power saving, right? So the idea was, as I mentioned, with a couple of AA cells, can you last for years for some typical use cases? These are very low data rate use cases. For example, the sensor might wake up and send data once a week, for example, right? So with those types of use cases, can you make the battery last for 10 years, for example, right? And a lot of enhancements went into LTE. So one good example of an enhancement was what's called this enhanced power saving mode. So the idea was that you can sort of just pretty much disconnect from the network, right? I mean, not completely, the network still knows about you, but the mobile is almost completely disconnected from the network, and it can do so for hours, right? And maybe after tens of hours, it lets the network know, hey, I'm still here, I'm still reachable, right? So you can see that with that, you can start to get a lot of gains in battery life, right? The other interesting thing that was done was basically better coverage, right? And a lot of demand for more and more coverage, because you want to be able to reach these devices that are embedded in your basement, that are sitting in sort of other areas that are very hard to reach, right? In fact, just take your smartphone and if you live in an apartment or something, right? You will see just go to the middle of the apartment, very hard to get a signal there, right? So, but then how do you make it work for these types of devices, right? They really need that coverage, right? So then a lot of techniques were added, the ability to handle many more repetitions was added. That's a simple way of sort of getting more coverage, right? So LTE took a big step towards it, right? But what's now happening is that with sort of the newer standards, 5G and so on, we are starting to add even more enhancements to it, right? So for example, one thing we are doing is this thing called mesh networking. So there's a lot of interest in this. So the idea is that if instead of having a one hop to try to reach the the IoT endpoint, you could break it up and maybe have a relay in between, right? So again, conceptually, it seems like can be done, right? Seems simple enough, but when you get into it, there's a very hard problem to solve, right? Because if you look at typical mobile technology, it has all these protocol layers, starting from physical layer all the way to the upper layers, right? You really have to manage all of those. You have to kind of break that protocol layering at some point, and then sort of glue it again. So fairly hard problem to solve, right? But if you can solve it, right, the promise is very interesting, right? Another interesting sort of technique that's come up, actually these kind of go together, is this technique of non-orthogonal multiple access. So for some of you who may be familiar with CDMA, right, it's kind of like a CDMA uplink in some sense, right? And the idea is that the mobile doesn't need to wait for a grant to be able to send data on the uplink, right? And of course, what this does then is that it will naturally cause collisions, because the same resource, if multiple mobiles try at the same time, they're going to collide, right? But then if you do it in a way that where this is sort of where the provisioning of this is good, you can minimize such cases. But the advantages are very good, because now what happens is that you can basically reduce latency further, because you don't need to wait for a grant. Because you can reduce latency, you can also reduce power, right? Because now your transmitter and receiver need to stay on for a much less amount of time, right? So all these advantages also come with that, right? So so these are some sort of other techniques that are being discussed, being sort of, and I think in the next maybe year or two they will find their way into the standards as well. So I hope that gave you guys an idea of what's happening in 5G. As I said, just to kind of summarize, 5G is really a basket of use cases, and sort of this whole gamut of requirements it's trying to address across enhanced mobile broadband, IoT, NCC, and so on. And as I mentioned, it really requires an umbrella interface to handle all these sometimes contrasting requirements as well. So I hope this gives you an appreciation of what 5G is trying to do. That's more than 3G and 4G. And as I mentioned, I hope some students here, you take away maybe a little bit better understanding of what we do in the industry, and why I think a lot of your skills are very well suited for some of that work.
Okay, let's thank Rohit for a very interesting talk. Time for some few quick questions. sessions, please restrict yourself to only one question per person, okay? Because we have to start the next session at 5:10. Yes?
Yeah, hi. My first question is, how do we maintain a balance between different problem statements or use cases? Like we have the problem statements of throughput as well as the power consumption. So there will be usually trade-offs. So how do we maintain that trade-offs to happen in the development of 5G?
Yeah, it's a very good question, and I think one simple way to answer that, though that's not always true, but one simple way to answer that is that we just build different mobile devices, right? So meaning we build, for example, the chips that go into your smartphone will handle one set of use cases, but the chips that we build for an IoT type solution will be completely different, right? Of course, the standard has to support both, but then what happens is that the mobiles can advertise that I am this type of device. It can tell the base station, hey, I am a enhanced mobile broadband device, right? So treat me as such. Or the IoT mobile can say, hey, I am this type of device, right? So that's roughly somehow.
Sorry, but second question is, what is the transition from LTE to 5G will happen from the end mobile user perspective? Like mobile user need to change their mobile phones, or it's like a support to the existing net device.
Actually, let me say this, right? I think most of us would change our mobile even without this, right? I mean, we typically change our smartphones every year or two, right? But yeah, this would come with a change of smartphone, right? I mean, you would basically need, and in fact, in lots of interesting ways, because what happens is that if you look at some of these millimeter wave type coverage, right? You need very, very specialized antenna design as well to make it work, right? So in some sense now and that has to fit in within the phone form factor. I didn't touch upon that because I was trying to not go into too many technical details, but that's a very challenging problem in itself, that antenna design and placement within a small form factor, right? So yeah, things are going to change, yeah, and they're going to happen soon.
So basically, with respect to the gap from Shannon limit, we have seen in some papers that LTE is about 5 to 15 or higher dB away from Shannon limit, and the bandwidth efficiency because of the control channel overhead is also 60% to 80%. So how are these numbers going to be in case of 5G? Bandwidth efficiency, control channel efficiency, and the gap from Shannon in dB.
Actually, where did you get this 5 to 15 dB number? That seemed really high to me, yeah.
So I got it from Preben Mogensen's paper, LT capacity compared to Shannon bound. This is paper published in Vehicular Technology Conference.
Okay, I have to look at that paper myself, but oftentimes it also depends upon what assumptions are being made, what data rates the paper might be targeting. It depends on a lot of these things, right? But maybe talk to me offline and we can,
And one more question is regarding...
we are running out of time, just give a chance to some other participants.
So my question is regarding the waveform that 5G will be using. So can you elaborate more on that, like how the waveform is changing from 4G to 5G? Like it's still OFDM, so what they have changed apart from numerology, that I understood. But apart from that, how the waveform is changing?
So few other things, right? I think so you're right. I mean, one thing is that the fact that it's scalable OFDM, that's similar, right? Some of the filtering techniques I didn't cover, then they are going to be a little bit different, and that allows both some more efficiency as well as some reduction in receiver complexity, right? Other than that, there is all this TTI structure that you saw, right? That's fairly different compared to 4G as well. Uplink is, as I said, see the thing about 5G is, right, it's a whole basket of use cases, right? So for example, techniques like what I mentioned, RSMA or NOMA, they are being discussed as well. And they are not contention free, they are contention based uplinks actually, right? So those are fairly different from LTE as well.
Okay, final question.
So recently, like telecom ministry has directed like 30-digit M2M devices. So will they follow the traditional LTE, or they will follow the standards of IoT designed by CCTV?
Yeah, I heard about this too, but I don't think I know enough about this to be able to answer this question. Yeah.
So what is the similarity between academic research and industrial research?
I'm sorry, what is your question? What is that?
Similarity between academic research and industrial.
It's a good question. Yeah, I think one can have a long discussion, but I'll just say one or two things on it. So I've been on both sides, right? I've done some academic research in a different lifetime, but I think a lot of academic research is very very useful, right? Because a lot of the fundamental concepts end up coming from there. I think what industry is very good at, right, is taking that and making that into good engineering, right? So in fact, a lot of times what we do, right, and this is what I was trying to hoping that maybe some students also take away, is that it's as much fun coming up with new concepts as it's taking concepts and making them work in the field. And what that requires is digging through logs, digging through lots of data to see why something is not working the way it's not working, and so on, right? So I think the industry is very very good at that latter thing, right? Because that's really the step required to take concepts to reality, right?
Let's thank Rohit again.